Hi, my name is Emmanuel Gianuzzi, and I'm going to present some preliminary results about numerical studies of protostellar clouds. I'm working with Federico Stassicin at IATE here in Córdoba. Stars form in dense core in molecular clouds due to the fragmentation of these clouds. This process is highly dynamic and chaotic. Through this talk, I will always refer to the formation of low-mass stars, more precisely lower than 8 solar masses approximately. The perturbation that triggers the gravitational collapse can be external, such as expanding H2 regions or cloud-cloud collisions, or it can be internal, such as the intrinsic turbulence. In this work, we focus on this internal process. Different studies of turbulence in molecular clouds show that they are in near virial equilibrium and their gas flows are compressible and supersonic. This turbulence lays between the Kolmogorov and Berger's models of flows. The fragmentation of a molecular cloud is an important process that explains why only a small amount of the cloud gas turns into stars, and why many stars are in multiple systems or in clusters. This process relies on the fact that, during the global gravitational collapse of the cloud, some regions within it may start to collapse independently by self-gravity, creating multiple star formation regions inside one big cloud. After many protostars have formed, they begin to interact gravitationally. This process may lead to the disruption of the cluster of protostars and creation of pure multiplicity systems. This fragmentation process can occur at any moment, assuming that the main effect against a collapse is the thermal pressure, and assuming that the collapse can be modeled by a polytropic equation of state, then the collapse can be approximately divided into 4 stages. In this case, the fragmentation can only occur during the isothermal first collapse, before the first core creation, or during the transition second collapse, right before the second core formation. In order to study the evolution of different star-forming clouds, we performed Sph simulation using the Gizmo code. This code can handle supersonic turbulence, self-gravitation, barotropic equation of state, and star formation. The numerical feature to model star formation are the zinc particles developed by Bate and collaborators in 1990. These zinc particles are, as their name says, particles that can swallow other particles. They only have mass, linear momentum, and angular momentum as spin. To implement these particles, we imposed different creation and accretion criteria. Without getting into details, a gas particle may transform into a zinc particle if, at least, its density is above this crucial value, 10 to the minus 11 grams per centimeter cubed. On the other hand, in order to be accreted by a zinc particle, a gas particle must be at least closer than 5 astronomical units to the zinc particle. It's important to remark that these zinc particles aren't stars due to the lack of temperature, feedback production, stellar evolution, and other physical processes. They are particles that can swallow gas and are used to model creation and accretion of protostars. Three different barotropic equations of state available in Gizmo, typically used for star formation simulations, are the isothermal, the VO3, described in Bate and collaborators 2003, and the F14, described in Fedrat and collaborators 2014. These three models try to mimic the variation of the polytropic index during the cloud collapse. The initial conditions were generated with the code Turbulent Cloud hosted in GitHub. This code creates an spherical distribution of particles with some user-defined parameters, such as a radial density distribution, the velocity power spectra, the total rotational energy, among other features. With this code, we generated 6 different initial conditions. All of them has the same initial number of particles, mass, radius, temperature, are homogeneous, and have a free-fall time of almost 0.2 million years. The parameters varied between initial conditions are the initial velocity, power spectrum index, -2, -4, and -6, and the ratio of turbulent to gravitational energy, 0.5 and 1. In total, 9 simulations were performed. In this table, I show the different parameters of each simulation. The alias of each simulation is created by joining the value of kappa, then alpha, and then the equation of state. In the next slides, I'm going to show some GIFs created with simulation snapshots, which are important for visual analysis and comparisons. Here, I'm showing 3 different simulations with the same value of alpha equals 1 and different value of kappa, 2, 4, and 6. We can clearly see that the kappa 2 simulation has a very different collapse respect to kappa 6 and kappa 4. Kappa 2 seems to be collapsing almost homogeneously, while kappa 4 and kappa 6 seems to have disrupted from the beginning of the collapse. Comparing between simulations with same value of kappa and different value of alpha, we see that for the kappa 2 simulation, there is not a visible or clear difference between them. Both of them seems to be collapsing almost homogeneously and forming stars almost at the same time. For kappa 4, there is a slightly difference between the simulation with alpha 05 and alpha 1. This difference can be seen just about the beginning of the collapse. It seems that the kappa 4 alpha 1 disrupts itself a little faster than its counterpart with alpha 05. This difference in time to get disrupted is seen more clearly in the kappa 6 comparison. In this case, it's more obvious than that the kappa 6 alpha 1 has been disrupted faster than the kappa 6 alpha 05. This disruption time seems to be correlated with the amount of kinetic energy that the cloud has at the beginning of its collapse. On the other hand, comparing between simulations with same value of kappa, alpha, but different model of equation of state used, again, we cannot appreciate any global or big difference between the simulations. It can be seen that the amount of zinc particles created by the isothermal simulation seems to be higher than its counterparts, but looking at the global evolution, we can't see a big difference between them. Comparing the time of the first zinc formation in every simulation, we found that the simulations with same initial alpha can be grouped into this particular classification. The kappa 2 formed the first zinc particle first, then the alpha 05, and finally the alpha 1. Analyzing the kinetic energy and thermal energy evolution, we can see that both K2 simulations rapidly transform part of their energetic energy into gravitational, and after a freefall time they rapidly gain high amount of kinetic energy. This is a consequence of the nearly homogeneous freefall. On the other hand, the other simulations tend to maintain a near global kinetic Birren equilibrium. Analyzing the thermal energy, we can see that the variation from a globally constant temperature system begins to be noticed right before the first sinks form in each simulation. We can also notice that there is an appreciable difference between simulations of different equations of state. Depending on their average sink formation and accretion rate, the simulations can be grouped into this particular classification. The lowest rate corresponds to the kappa 6 simulation, then the kappa 4 alpha 1, followed by the kappa 4 alpha 05. Finally, the kappa 2 have the greatest formation and accretion rate. The values were calculated applying a linear fit to each curve. Here we show the variation of the power spectrum through time in three simulations with different initial power spectrum. We can see that all of them evolved their power spectrum into one with power index equal to -4. This is consistent with the compressed fluids model of Berger. Comparing the initial sink positions distance between simulations relative to the center of each cloud, we can see that both kappa 2 simulations form their sinks very near to the center of their clouds, while the K6A1 formed them almost at 0.15 parsecs from the center. It can also be seen that the kappa 4 simulations tend to form the stars at a radius between these two. In order to determine the clamps formed in the simulations, we used an algorithm described in Rudick and collaborators 2018 composed by these three steps. Here we can see the amount of clamps at 4 different times. The line filled part of the bars represent the clamps that have at least one star within them. Here we can see that the number of clamps doesn't vary between simulations with different equations of state before they form zinc particles. On the other hand, in order to determine the sinks system formed in the simulations, we used an algorithm described in Bate and collaborators 2009 composed by these three steps. In this table, we can see the multiplicity and companion fractions calculated in this way, where B is the amount of binary systems, T is the amount of triple systems, and so on. These values are obtained for different control times in order to be able to compare their values between simulations. Comparing these values to the ones obtained by observations, we found that only 2 of our simulations produce an MF similar to the observed, and only 1 produce a CF similar to the observed. These differences may be a consequence that we did not impose a maximum multiplicity for the system formed as usually done. When it's done, it's usually a value of 4. Summarizing, we performed 9 simulations involving 6 different gaseous clouds we created as initial conditions. These simulations vary in the initial value of kappa, alpha, and or equation of state used. Then we made comparisons and analysis of the evolved clouds related to their accretion rate, power spectrum, and other characteristics. We are currently continuing with the clouds evolution, expecting to reach 2 freefall times in all of them. We are also looking forward to create and evolve new clouds with different radii and mass in order to have more parameters for comparison. Besides, further and deeply comparisons with observations must be made. That's all. Thank you.